unconstrained, what is the pressure in that jet? Do you have to think?
Atmosphere.
Atmosphere. Yeah, atmosphere. And as a statement for the problem, you are told the frictional head loss is given at this stage as 7 meters of water. Now, if I'm scratching my head and say I don't have a feel for what is meant by 7 meters of water, can someone help me to convert that to PSI? Because PSI I can see that there's a pressure drop, like 10 PSI pressure drop. So I can relate to that due to friction. If you are given a length, just a length of water, or a length of millimeter of mercury, like atmospheric pressure is how many millimeter working? 760. How do you convert that to actual Pascal or PSI? What do you multiply that height by, or length by? Rho G. What rho? If I give you in water or in mercury, what rho will you multiply by? Mercury density. So when I give you a pressure in terms of, or rather a height, a length of water, and I say, well, I really cannot have a physical feel for it. I want to something in terms of PSI. How would you convert that? What would you multiply that by? Rho G. In this case, the rho of water. And that's part of your homework. One of your homework problems give losses in terms of inches of water, and that's how you have to convert that. So this is given at this point. When we're done with this in-class energy equation application, the remaining lecture and the next one is how one can actually estimate by way of Moody diagram. If you tell me the size of the pipe, what that frictional head loss is. So at this point, it's a given, but later on our job as a fluid hydraulic engineer working for Exxon is to determine what actually, how much pressure loss due to friction. And that's the contents of chapter 8. Okay, so I think with all that, the problem is defined, and I asked you last time, do you agree with the physical interpretation, which is the energy added in the pump, the power added in the pump is to overcome what now? Gravity of 2 meters. This is physics. This is something I want you to get used to and be able to think and discuss it in layman terms. What else? Say that again? Friction, yeah, friction, right here. One more last term, which I mentioned last lecture. What? Kinetic energy. This nozzle. Okay? So, I should mention some constraint with this energy equation on the left, and we'll go over all the assumptions later when we derive the equation from first law of control law. It's assuming steady flow, this is go without saying for the whole semester, and incompressible, no change in density. The energy equation on the left is under those constraints. So if I apply that, between point 1 and point 2, and here I want to slow down to challenge you to tell me what are the signs for the shaft work, as well as what is the sign for the frictional head loss, H sub F. Start with the easier one first. What is H sub F according to the problem statement? 7 meters. Plus or minus? Always plus. Here's tricky. I have a pump. H sub S stands for shaft work. What sign would you put? Negative. Negative. So I will replace this with negative HP, stands for pump. That sign is very important. Wrong sign, wrong answer. Where do you pick point 1? Point 2 is here, which is a free jet, so this is PA. Nothing different than what we did with Bernoulli, but this is, again, not Bernoulli. Tell me where you pick point 1?
In the reservoir?
Where? In the reservoir, yes. Where?
Like at the top of the reservoir?
At the top of the reservoir here?
Outside.
Outside, very good. Why? Because the pressure there is ambient, atmospheric, and what can you tell me about the velocity at that point far away from the intake? It's zero. Too small to be of any consequence. PA. So those are all repeat. You don't want to do the intake because you don't know what the pressure is. It's nothing but atmosphere, because it has to be less to suck the water in. All right? So the change in the elevation, change in Z, here is 2 meters at point 2. So I have just slight rearrangement of the equation. H sub pump is now replaced with the appropriate sign of specific work divided by gravity. Right, and move it to the left side of the equation just to keep all the term positive. Velocity at the exit is unknown that I'm trying to solve for. I have the change in elevation of 2 meters and the Hess loss due to friction of 7. That gives me 9. Now tell me how you finish the problem. What haven't I used yet with the given problem statement information? The power, exactly, power. The 30 kilowatt is what determines how fast that jet will be after overcoming friction and after overcoming the change in elevation. Power. Are we good? Anyone been to the graduate student center next to the bookstore? You know what I'm talking about? They have a auditorium. I think most of you are 20 or 18. So there was a flooding, I don't know how many years ago, maybe before you were born. The whole War Memorial Gym, ground level, and that auditorium was underwater. That auditorium was underwater. So just before you were born. And there's a transportation museum in Mona, where they had a big locomotive. It was washed out. Once in a century festival. Yeah. Okay, anyway, back to water. So the last link is how I make use of that 35 kilowatt to the specific work. So the answer is on the far left. What is that equation? What's that equation? Right here. To get power in kilowatts, I need to multiply the specific work by m dot. And m dot is given by rho VA, continuity. Continuity, you use that. You use it now almost by default, almost without thinking. But you did use it. And that's how I can relate to the exit velocity VE in this whole problem. So the next step, that's all the physics. The next step now is algebra. So continuing on for a pump, power added just recopy that equation on my left. And what I'll do is to substitute this specific work with this equation so that my equation will look like left-hand side is now become right-hand side but unchanged. Kinetic energy plus 9. The 9 comes from 2 plus 7. Replacing the specific work, take a little bit of algebra. It's not difficult. So this algebra just show you how I replace the specific work by the continuity and the power equation. Rho VA is now all in the equations. Any question at this step? Yes?
What's the velocity you use there?
This velocity V sub E,
Yeah.
yes, to go back to where I am here. So I had used point 1, which is far from the intake, and point 2, which is at the nozzle exit. What is this V2 then? What is this V2? Well, where is 2? 1, no, where is 2? 2 is right here. End of the nozzle, where pressure is atmospheric for free jet, so V2 become V exit. The unknown I'm asked to calculate. What? So that's how I relate the kinetic energy to whatever energy can put in from the pump, minus the change in elevation and minus the friction. Yes?
So for that velocity, since it's a little bit, it's farther down from the pump, so if the pump was, say, before the bend, would we not be able to use that same velocity?
No. Continuity is continuity. I want to make sure everyone understands the question. Right? So if I put the pump here, instead of here, will I change the problem? Is that what you're asking? Yeah. What's the answer? No. Absolutely not. Continuity is continuity. What comes in must go out. So it doesn't matter where I place the pump. Very tricky question. We'll come back to that. Okay? I want to make sure you solid foundation on continuity. You will come back and haunt you. Trust me. Other questions? So I have, but now if I put in the numerical value, power is 45 kilowatt, density of water I know, diameter is 5 centimeter, etc. And then on the right-hand side, I plug in all the value, I get 1821, it's just all calculated. So make sure you get the right unit. Right, so that step I'm skipping. Any question up to this point? Any questions? This again comes from all these parameters. Numerically, if I plug them in, I get 1821. So, let me rewrite this equation. Again, I'm a little sloppy to skip the unit. But they're all now in meter. I have this equation that has velocity squared on the left and velocity in the denominator on the right. Any suggestion how you may solve this? How many unknown and how many equations? One equation, one unknown, but it's not an explicit equation where I can solve the velocity directly. What would you do to solve the exit velocity? Any guess?
Multiply everything by VE, so you have like.
You still, other than VE, you still don't have an explicit equation.
With the roots, cubic function.
You still don't get it. It doesn't work as simple as you think. Yeah. It turns out the easiest way, not necessarily the easiest, is by try and error. guess the velocity. And then if they don't satisfy the left-hand side, the right-hand side, guess another one. Until they converge. And then it turns out the velocity in doing that way is 31 meters per second. There may be other way that you can program it and solve it in MATLAB or other way, but trial and error is fairly straightforward. So, point being, not the detail of the algebra, but point being, you understand the physics. You understand what's going on. This example plus the homework of which direction the flow will go is very critical in terms of understanding the use of the energy equation. Energy must be conserved. All right, questions on this homework? On this example? So as far as the example goes, if it's not water or oil or petroleum, if you're dealing with air jets, how can you simplify the problem further? What's the difference between air and water and oil? What can you neglect? Gravity. Tell me why? Why in gases?
Because it's typically assumable that their density is low enough that gravity won't affect it.
That's it. Density is small relative to the other terms of the equation. And the same example I gave many times, the pressure difference between my foot and the ceiling in air is negligible. Change in 10 feet of height, I don't care. So for any gases or air, the takeaway is forget the gravity term. Now for the remaining lecture today, we're going to set up and ask ourselves, how can I use the Moody diagram to estimate this 7 meters? And you can see how powerful it is once you can do that. Then any flow system I gave you, your dormitory, 10 floor of buildings with water, plumbing, pipe, etc., and the pump to get water at any level. When you open the faucet, you have water coming out. You can determine what size pump is needed to make sure you don't have a water problem on the 10th floor. In the petroleum industry, how do I have a pump size enough to pump gasoline over a distance of 10 miles, for example? Okay, so at that point, this is not needed to be a given. Instead, you tell me the flow system. Tell me what pipe you use, how big, how fast you want to pump it, and I will use the Moody diagram and give you the answer. All right. So one last question before I move away. So you have seen this equation of energy. If I tell you to neglect friction, forget that 7 meters of water loss, say 0, will the exit velocity go up or go down? No, it will be greater than 31, equal to 31, or less than 31. You shouldn't have to think much to answer that question. If you understand the physics I've been emphasizing, it should be just like that. Why is it good? The answer is greater. Why is it greater?
Slow it down.
The friction, the amount of friction that has to be taken from my useful work is gone. So the same 35 kilowatt can now pump more fluid at a faster rate, higher kinetic energy. And that's how you can speed. And we work this problem in 5 minutes by making the 7 meters 0 And the answer, exit velocity is about 2 meters per second faster due to the effect of the frictional effect. Okay, so much for energy equation. There will be more homework that continue to challenge you on that. But right now, let's deal with the origin of the Moody diagram, which is one of your homework problems. To do that, let me set up an example which we will not start today because it will be next lecture before we tackle it. But it's a good motivation to see how practical problem can be solved using the Moody diagram. So you're now an engineer working for Exxon, and they hire many of our graduates, as you know, probably through Expo. And they pay very well. So gasoline is the property, less dense than water. And I want to transport gasoline for 15 kilometers, 18 centimeter diameter pipe. And I have to tell you how fast I want to pump it. Obviously, the energy equation relates to how fast you want to pump the fluid. The faster you want to pump it, which may affect the amount of friction, the more power you may need. So the flow rate for this problem is about 0.2 meter cube per second. Which, when we lose continuity, is about less than 10 meters per second. Not very fast, but very practical. 10 meters per second is like 30 feet per second, so you have a feel for how fast it's moving. I leave a space here because I do have to tell you what kind of pipe. It's called cast iron pipe. Cheap and lasts long. So 15 kilometers, unless you are from Europe or other countries, is not very